At present, so let's go on with the program. It's exactly on 9 o'clock, so we're only 5 minutes late. So the next speaker is Aureila Chenu, who's now in Luxembourg. And this is a contributed talk. So Aurelia, it's 25 plus 10. So I'll give you a sign, or I guess can you see the chat?
I can. If I don't, please just.
Yeah, I'll give you a notice 5 minutes before. But so it's easy now since it's exactly 9. So at 9:30, you still have 5 minutes. And of course, if there are interruptions in the middle, and people can, of course, ask and interrupt, that's fine. Then I'll give you some extra time like I did for Ali. So I think we'll be fine. Okay, so you'll be discussing this work on shortcuts, which is really interesting. It's actually related to this open quantum dynamics. So please go ahead.
Thank you. Thank you very much, Tapio, for the kind introduction. And thank you for the organizer for giving me this opportunity to present this work that is in collaboration with quite a number of participants here. So with Tapio, Ali Resakani, Sahar Alipur, a PhD student in the group, Léonce de Pays, and Adolfo del Campo, that is also at the University of Luxembourg. So very short, as Tapio mentioned, I just moved at the University of Luxembourg from Bilbao. So we are currently on the campus. The physics department is currently in the city center. That is beautiful. And we are going to be relocated at some point in time in the new campus in Belval at the border with France. So that is being constructed at the moment. Let me take this opportunity to show, I think the organizer really helped promoting this special issue that I am organizing with David Sueco. So if you have any contribution, we'd be happy to have them in entropy. So the topic of my talk is this shortcut to adiabaticity, which I will not introduce in much detail here, but that allow tailor excitations during a dynamic. And most of the work until now have been focusing on unitary dynamics. So one of the useful applications is in this framework of quantum thermodynamics to help deal with increasing efficiency while operating at high power. So I want to focus here in the open cycle that's helpful thermalization, and where you need to have a dynamic that is open in order to fasten this thermalization. So that's the motivation of our work, and I will present this control scheme to fasten the dynamics of open quantum system, first in a general setup for an arbitrary given trajectory, and then focusing in a setup of a harmonic oscillator to do controlled thermalization and controlled squeezing. If there is time, I'm not very sure, but I would like to very briefly introduce some results on the entropy-based definition of heat and work. So let me start with this shortcut to adiabaticity, a very brief review, and I will focus on the counter-adiabatic driving. So imagine that you have a system that is being driven by a time-dependent Hamiltonian, and that has this instant diagonalization here. Then the adiabatic approximation gives you the time-dependent solution and evolution. The question that was asked like some time ago already by Demir, Black, and Rice and Berry is there a Hamiltonian h of t that is for which the adiabatic approximation is a solution of the dynamics? And the answer is that the original Hamiltonian that was in the driving system, needs to be corrected by this so-called counter-adiabatic driving that allows parallel transpose so that each eigenstate remains an eigenstate of the instantaneous Hamiltonian at any time t. And this is the correction that needs to be implemented. So this has been very successful in developing like control techniques. And it has been implemented in a number of experiments, starting with a single particle, then in a BEC that they removed the mode of breathing and sloshing, so you can see the control dynamic versus like the non-control dynamic where there's more distortion of the BEC. Then in a 1D quantum fluid, there was experiment as well, and we implemented in a unitary Fermi gas, so strongly interacting Fermi gas. So this is the case like in this dynamics, all the systems have been considered isolated in the sense as non-interacting with any environment. And the question that we ask is, can we control systems that are interacting with the environment? So this question was considered like some time ago in the group of Black-Vedral, and mainly looked at in the context of Markovian dynamic, where they use adiabatic definition of adiabaticity in Liouville surface space. There was also a specific system that have been looked for, mainly thermalization of harmonic oscillator, and I will be detailing one of these. And together with Sahar Dalipur, Ali Rezakani, and Adolfo de Campo, we came up with a general setup that is independent of the coupling with the path and of the trajectory. And this is what I like to focus on. So we assume that the trajectory is arbitrary in the sense that it can be written with this instantaneous diagonalization. So it is straightforward to write the master equation where we have a dissipator. And the question is, how can we implement this dissipator? It is the same case as the unitary parts. Sometimes the counter-diabatic Hamiltonian is easy to write, but hard to implement. So here we are focusing on writing this counter-diabatic dissipator. The first physical implementation that we can find is through a non-emission system. If the time-dependent Hamiltonian is the counter-diabatic term that is obtained from the unitary dynamic and some corrected term that is in the form of gain and loss, this I gamma t, then the equation of motion can be written as follows. And if we choose properly the gamma of t, that would be given as the time dependence that depends on the derivatives of this eigen values of the trajectory, then we can write the master equation here that will reproduce the trajectory of interest. Here we have also normalized the states so that we preserve the norm. So at each time t, there is a balance gain and loss. This was introduced like earlier in the context of Brownian graph for non-emission dynamics. So what it means here is that if we can implement this Hamiltonian in the lab and construct the norm preserving dynamics, then we will create this dynamics of interest. So that the first aspect to look at it, there is a second aspect that we can, a second approach that we can take, which is a non-Markovian dynamics. So the dissipator is just given by the derivative of these instantaneous eigenvalues of the trajectory. And if we write the projector here as a Lindblad operator and the time dependence, if we take this particular time dependent rate, then we can write a Lindblad-like master equation that is of this form. So it looks like Lindblad, but importantly, the gamma here are generally time dependent and generally non-Markovian. So this formalism gives answer of like which kind of trajectory, how the master equation could be implemented in the lab.
Excuse me, the interruption. Is this equation also nonlinear in some way as before for the
So the equation is
and if not, how can it come that it is linear in the non-Markovian case and then non-linear in this Markovian non-Hermitian case?
That's a good question. So let me try to, I did not think about it earlier. So what I can tell is that earlier it's non-negative, it's non-linear in the state, right? So it will be non-linear in the density matrix here, and we need to do this non-linearity so that we preserve norm. Now, in the other case, the Lindblad operators are given directly as a projector of the state. So this M and N are directly the one diagonalizing the trajectory of interest. It is written as non-linear in the state in some sense, but
it is non-linear. It's
yes,
non-linear. The equation is non-linear. It's obvious, yeah.
Yeah, since the L are directly related to this.
They are functional project. Of rho. Yeah,
exactly.
So the whole thing is nonlinear.
Which makes it hard for implementation. So this is a formal presentation, but then the question is how can this be used in the lab for implementation of the trajectory? And this is what I want to detail afterwards for a specific case of a harmonic oscillator. So the question that we ask is, can we thermalize a harmonic oscillator that would require going from an initial state to a final state? But here we cannot rely on parallel transport anymore because we need to redistribute eigenstate population from the initial Gibbs state to the final Gibbs probability distribution. So we want to do this fast or in a controlled time, and we want to find a scheme that we can implement in the lab. Let me set up the problem from a different issue that I will explain how it relates, but let me also introduce at the same time the squeezed thermal state. So let's say that you start with your thermal state of a harmonic oscillator that I have written here, and you want to go and generate a squeeze state that's at a different temperature. So the squeezing operator that I'm looking at is something defined with the amplitude R and the phase phi. That's a measured correlation between position and momentum operator. And the state that I'm interested in constructing is this squeezed thermal state where I have defined this dimensionless parameter that comes as function of the trap energy and the temperature. So this is actually related to thermalization of a harmonic oscillator, and it's well known, and that's why I'm introducing here. So if you look at this squeeze states where you have no correlation at the end with x and p, so phi equals 0, it's actually the same as implementing, as doing the thermalization I was just presenting before, in the sense that you would create, so here you would create, if phi equals 0, this general harmonic oscillator Hamiltonian just is a time-dependent harmonic oscillator, and we end up with this problem. So let me focus on this thermalization of a harmonic oscillator and generating squeezing at final phase of 0. So the trajectory of interest is, again, this one where we now know the lambdas and the counter-diabatic Hamiltonian for this. So these are the Fock state of the time-dependent harmonic oscillator. And they evolve with this counter-diabatic Hamiltonian that is well known as a squeezing term. So you can have here minus omega dot t over 4 omega t, or you can have here just the derivative of this squeezing parameter that controls the amplitude of squeezing. In general, the way to implement this trajectory is to go in a rotating frame rotated by x squared that allows you to kind of kill this counter-diabatic term and allows you to implement this this trajectory by just like changing the frequency of your trap. So in this case, the trajectory is closed, it's unitary, and the state in this rotated frame is just controlled by this time-dependent harmonic oscillator. The entropy here, because I'm looking at a unitary system, is constant, and the eigenvalues here are also time independent. So let me show you like which kind of states one could construct with this, and this is no new results. So I just want to present like a map of like the accessible states. That's the final inverse temperature over the final for the initial inverse temperature. And this is the final frequency over the initial frequency. If you have no production of entropy in your states, and this is for the case where this ratio epsilon equal h bar omega beta is constant, then you can access like any state, final state on this isoentropy line, meaning that you have to conserve this constant ratio. This can be done if you implement the time-dependent harmonic oscillator, where the trap frequency here is a controlled trap frequency that is given by the reference one. That's the reference trajectory that you choose, that you would want to reproduce the adiabatic trajectory, and the correction. The correction is this adiabatic scaling factor that is just the ratio of the frequency. So now let's consider that you want to access more than these states, in the sense that you want to allow for change of entropy. And in this case, you would make this epsilon time dependent. If I come back to this slide here, how does it change? Well, now my eigen values for my states are starting to be time dependent. The entropy is time dependent, but importantly, we get the dissipator. So the dissipator is just the same form as I was writing formally in the general setup. In this particular case, we can write it this way here. So we still want to find something that we can implement in the lab. The first idea that is proposed in this PR was to write an engineering dephasing in position. So we assume that the master equation is written in this form, where we have the same unitary dynamics, and we just took a dissipator that was stochastic, well, that was controlled dephasing in position. Then we actually showed how there is a more general master equation that you can write just to generate this kind of states, and how this is a particular case of the general master equation that that you can choose. I will focus on this for the purpose of like illustration. So if I come back to my map of like initial states that are now available, I have this epsilon that is time dependent. So it's as function of like the reference trap frequency and the reference temperature. And so before we were looking at this isoentropic line. If I add dissipation to this term, then I have access to cooling and heating. So this is phase-space cooling, where we really shrink the state in phase space, and this is phase-space heating. The difference is given by the sign of gamma, with it is negative or positive, which controls the sign of the entropy production. Now, interestingly, how does this open dynamic change the control parameter? First, we have two control parameters. We have the, well, we still have the control frequency, but we have the dephasing. The control frequency that needs to be implemented in this case of open dynamic is now changed in this form. So we still have it as function of the reference frequency and some correction. So if you remember before, we had like this adiabatic factor that was given by just the ratio of the frequencies. And by opening the dynamics, then the frequency needs to be also corrected by this factor here that depends on the change of temperature. So this is the first consequence of opening the dynamics. The second one is that you have an additional control parameter that is the dephasing. and that controls both. That depends on the reference frequency of your trap and on the temperature variations to this epsilon d. So let me quickly show like the we run out of time. So let me quickly show how you would do this in the lab. For example, if you choose this reference frequency of compression, then the reference that you would need to implement would be this red or this blue dot according to how fast you go the process, and that would be the gamma of t rate of dephasing. This rate does not depend on the final time of the amplitude of this rate does not depend on the final time, but just its maximum. So that shows the maximum. If I go very fast, then I have some cost associated with the shortcut that is measured with like the gamma of this, the maximum of this gamma. If we want to do cooling, then you can do the same. Basically, importantly, you need to implement a negative gamma of t. I'm going quite fast because I'm running out of time, and I do want to present like some other results. So if you have questions, I'd be happy to answer this like later. But how would you implement this in the lab? Well, it would be through like shortcuts. Well, we have two ways that we came up with. First is the stochastic parametric driving, where you would take your time-dependent Hamiltonian and add a noise. So this is a stochastic field in position with an amplitude that will generate your dephasing rate. Or you can do continuous measurements in the position with some time-dependent amplitude as well. In both cases, you have a stochastic master equation for like for the density matrix, and if you take average of all realization of noise, then we can kill this stochastic term and end up with this master equation that we wanted to do. So what we've done so far is we've gone from a Gibbs state to another Gibbs state that and thermalize it thanks to shaking the trap. So in addition to doing the well-known time-dependent harmonic oscillator that generates squeezing, we've been shaking and adding some stochastic noise that allow us to control the temperature. In this particular setup, I did not show the Wigner function of the state, and I think this is also known in the community, but while you generate squeezing during this protocol generates squeezing, and at the end of the protocol, there is no more correlation between X and P, in the sense that for compression, for example, you would reduce the quadrature in position, but it's not possible, as far as I know, to control the phase. So this is what we've been looking at. Can we do the same? But in addition to controlling thermalization, we also want at a given time to be able to control the phase of the squeeze state. So for this, we have looked at this in the frame of a two-photon Raman Hamiltonian that is also known as a technique for implementing squeezing. Very briefly, this is the Hamiltonian that we work with. So with the a two-level system, the vibrational degrees of freedom and interaction with the lasers, two lasers. It allows to generate some effective Hamiltonian here that creates this nonlinear interaction, and for which the master equation is known as depending on this alpha parameter here. So importantly in this framework, so alpha depends on the laser amplitude and relative phase here. If we look at the squeezing amplitudes, it is directly related, its variation is directly relating to the norm of this constant alpha. So if you wait linearly in time, you will have a linear time dependent of this squeezing amplitude, but you can do reverse engineering so that you control this of t as for a defined time, and this is what we do in the shortcut, and this is what is shown here. So the non-conventional techniques, I think, have to wait a given time to generate this squeezing parameter, and we do some reverse engineering so that when we have fixed our final time, we can generate a given squeezing parameter. And so now what we want to do is allow for the change of temperature. And we start with the same as the equation with this dephasing in position that in this particular experiment can be recasted with this Lindblad dissipator here. And I'll just show you the results. You can see the detailed derivation in the manuscript. But this master equation allows to create the squeezed thermal state here at controlled, so amplitude, phase, and temperature. And we show that, so it is generated on the ground states of the electronic ground state of the atom. And that would be the squeezed thermal state that we solve by first factorizing in normal ordering the state. And here are the parameters that you will need to implement in the lab to generate the dynamics. So these are for cooling, isothermal, and heating processes. And this is the amplitude that's related to the laser amplitudes, and the kappa is related to the dephasing that you have. So the dephasing here is obtained by adding a stochasticity on the laser amplitude. Again, as in the case of just changing the trap frequency for cooling, we have that the dephasing needs to be negative for cooling and positive for heating. And that's the most drastic differences for the different protocols. Very good. So I still have some minutes left to present different topics that is related to the first point of this general scheme of open quantum system, and from which we propose some entropy-based definition of heat and work. So I come back to this arbitrary dynamics that is given as, and from which we assume that we know the instantaneous diagonalization. Then the internal energy is can be written as just a trace of rho THT, and the change is of internal energy is what we want to split into heat and work here. So in what I call the semi-classical definition, the basis of the Hamiltonian is taking us the reference basis, and then this gives two terms for the change in internal energy that are then assigned as a variation of heat and variation of work. There is another physical basis that we could say is relevant, is the one of the system eigenbasis. And in this case, everything that goes into the variation of the instantaneous eigenvalues can be assigned to a variation of heat, and that would be linked to variation of entropy. And the remaining term is work as before. But there is some part that was originally considered as heat in this more kind of standard approach that is now assigned to work. What is this parts coming from? So this is based on the standard approach, on the general scheme that I introduced for this trajectory-based shortcut to adiabaticity, where we have this instantaneous diagonalization of the trajectory, and we choose the unitary dynamics to be defined by the counter-diabatic Hamiltonian. The remaining terms are the one that depends directly on the variation of the eigenvalues of the trajectory. If we do so, then how this choice influences, or how the splits of the changes of internal energy, well, we have all the terms that depend on the derivative of these eigenvalues that we assign as heat. So these are the one that change the entropy. That's why I call it entropy-based definition of heat. And then we have the remaining terms. One of the terms is just the one that is the work, because the system is being driven by a time-dependent Hamiltonian. And this is the term that can be shifted, or we are proposing to shift it in and assign in work instead of heat, in the sense that this is the work being done to stay on the driven trajectory. So again, this is some proposition, and really the argument is to relate everything that is entropy variation into heat. Here, very quickly, and this is my last plot, is an example of an atom in a Markovian path, where we can see the variation of internal energy as split in with heat and work. And interestingly, I want to highlight this inset where the heat variation is directly accounting for the variation of entropy. So with this, I'd like to come just to my conclusion and give some take-home message. So I started with presenting a universal scheme to implement, to find formal definition of shortcut to adiabaticity in open quantum system. We found some application for fast thermalization of harmonic oscillator, how you would need to create an experiment for the implementation. And this is related to a well-known experiment on just like controlling the trough of a harmonic oscillator that generates squeezing, and we can create, I generalized it to engineer a setup where you can control, in addition of the thermalization, the squeezing angle, controlling the momentum and position in your state. And in the last part, very quickly, I propose this, or just show this entropy-based definition of heat in open quantum system. So again, let me thank my collaborators. So this was done with Sahara Lipur, Ariel Sacani, Adolfo Del Campo, a PhD students, Leonce Dupey, and also Inigo Egosquiza in Bilbao. And I'll just drop this advertisement. And thank you for your attention.
Thank you, Aurelia. We're just a few minutes late, so I think we have time for some discussion, and I will try to stop in less than 5 minutes. And then I would actually suggest, if you can, stay on the chat and you can ask further questions on the chat. There were some questions for Ali's talk in the chat, so that's one way of discussing, since we can't discuss in person. So let's go. Do I see any questions?
Yeah, I have a quick question.
Oh, sorry, yeah, go ahead.
Yeah. Hi, Aurelia. So you had given specific examples, so I'm not able to lock on to the kind of general point. So I just wanted to ask you this general question, which is, there should be a no-go theorem against being able to thermalize arbitrary Hamiltonians down to their ground states, right? So this is a well-known no-go theorem, that you can't cool arbitrary Hamiltonians to their ground states. So if I apply basically the shortcut method of thinking about thermalization, where does that no-go theorem present itself? So where does it produce basically the little hindrance that says, hey, you're not allowed to cross this line? Right. Am I making myself clear? Like, I mean, adiabatic quantum computing is the gap question. Closing.
So we have not looked at it, so I don't have the definite limits. What I think is that, so there's always a cost associated with these shortcuts. The faster you want to go, or maybe the cooler you want to go, you would have to implement like more and more or higher dephasing rate. So I think it would come in, well, some derivative or some maximum of these rates that need to put on that, yeah, sometimes. But it's a very, we haven't worked it out. I did not think of this before.
Yeah, so we had a paper on quantum control on thermalization from a couple of years ago. And this is something that I kind of worried about for about, a couple of months. We were just walking around thinking about this. So
yeah, so I think you would see it in the parameters, but some kind of like limit that can not be crossed. But I'm not sure how it comes, if it comes naturally. Yeah, so okay, definitely that's interesting.
But I think, yeah, you're giving a hint as to where to look. Yeah, thanks a lot.
Okay, are there any other? There's one question in the chat. Yes. I don't see any hands. Oh, okay, go ahead.
Thanks. So, hi, Aurelia. I was wondering about the final part where you gave these new definitions of heat and work. So I have a very naive question. So if you could go back to this slide.
This yes. one or before?
No, well, or this one that you had 3 terms, right? The next one.
With the, yeah.
So what I was wondering, like, imagine that you are not driving. So the last term is 0. So you are not driving your Hamiltonian, and you just have a system in contact with a thermal bath, which has coherencies. Okay. So would this second term be 0 or not?
Coherencies in energy or in the state?
Yes, well, yeah, what I'm trying to say is that maybe the effective basis would change as it thermalizes with the bath. So it's not clear to me if this term is 0 if you just have a non-driven system. That's what I'm trying to say. Because I would expect it to be heat, not, I mean, if like.
Well, if you're going adiabatically, then I think you will not have any of this work term, like the one in the middle. So let me try to see.
That's why I was saying that you have a state that when it thermalizes with a bath is also somehow getting dephased. So
yeah, but I think it's the one in the middle will also not be there.
Yeah, I think it will vanish, actually.
Yeah, I'm less sure because so that your definition is that you are in the instantaneous. So you would take for a given time and diagonalize the system in the instantaneous basis. So I would expect that for a thermalization process where, I don't know, you are, for example, killing the coherencies, this instantaneous basis will change as well.
Yeah, but if you go adiabatically, I'm not sure. We need to work it out. I think that this term in the phi dots h would vanish, but
okay,
that's something. Yeah.
Yeah, it should. Yeah, but of course, yeah, maybe difficult to see it directly, but we should look. It's not a difficult
I don't remember
calculation.
if we worked it out, but that's a good check to do.
Yeah, it's a good check to do. Yeah, I think it will vanish.
Okay, yeah, I would make
it should. Right.
Yeah. Okay, so I think we'll move to chat again. Let's have a short break, and then we continue with the last invited talk.
Yeah. So let's thank our speaker.
Yes.